Hello, everyone. Welcome to the presentation of orbits, an efficient streaming algorithm to recover missing values in time series data. So let me just jump right into the motivation of our work, and let's consider monitoring systems used in sports, such as in soccer. So during practice, players are equipped with sensors which record different measurements, such as the position of the player, their performance, the accuracy of the passes, the interaction between each other, and so on. So what happens is that the players run, and of course they push each other, causing the sensors to fall and stop recording values, creating missing values in the data. It's extremely important for coaches to be able to monitor the complete data in order to give on the fly instructions and adjust the tactics. In such monitoring systems, it's pivotal to be able to repair those data streams in efficient manner, because we are dealing with data of very high frequency, and also to be able to accurately recover large missing blocks. And oftentimes, those blocks follow different patterns. They could impact one or multiple sensors. They could be overlapping, disjoint, or any other pattern. Here I show you a graphical representation of our problem. On the time axis, we have the time. On the x-axis, we have the time. On the y-axis, we have the value. And we have 3 time series. In the black time series, there is a missing block that starts at timestamp 12. Which occurs at the tip of the series. So basic statistical techniques such as interpolation, which is shown here in red, are not able to properly recover large missing blocks because they cannot leverage the correlation inside the time series and across different series. Of course, there exists advanced techniques or streaming recovery techniques. And those techniques, they belong mainly to 2 classes. In the first class, one finds the techniques that rely on approximation. Those techniques are efficient, but are not accurate. And in the second class, we have techniques which compute different kinds of data dependencies. And because of that, they're able to achieve a good recovery, but they incur a high runtime. So in our paper, we introduce orbits, which is both efficient and accurate. So here I show you how orbits works. So we take the example of the 3 time series, and we consider, we take the example of one incomplete time series. Of course, orbits can handle multiple time series. So each time series is mapped into a column of a matrix. So we have the xt-1, which is a part of the matrix before the update, which corresponds to this part. And then this delta x represents the update, which corresponds to this part. So the first step, our technique computes what is called the sign vector, which is a vector that consists of only -1 and 1 as elements. And using this vector, our technique applies the centroid decomposition, which decomposes the original matrix into 2 matrices, L and RT. And by applying a dimensionality reduction, which reduces a subset of dimensions, we multiply the 2 matrices and we obtain an approximated matrix. And this approximated matrix contains the approximated missing block. So we take this block and we replace the original block, right? And we do this process in an iterative manner. So our goal here is to be able to compute or to infer the decomposition of this whole matrix based on the decomposition of the sub matrix before the update. So the way we do it is that basically we take the most expensive operation in CD, which is the computation of the sign vector, right, the Z. And we simply propose a technique that computes directly ZT out of ZT minus 1, right? And by doing so, we are able to incrementally compute the full decomposition. So our technique consists of three steps. So in the first step, we take advantage of an inherent property of time series, which is the temporal continuity, which basically means that the new data that is appended to the stream shares some similarities with the existing data. And we prove that the centroid of the new time series, right, or the updated time series is equal to the centroid of the time series before the update plus the norm of the stream updates, right? And this property allows us initialize the sign vectors, right? And what we do, basically, we take the sign vector before the update and we simply append 1. And by doing so, we are sure that we will reach the optimal sign vector. In the second step, we take advantage of a second property of time series, which is the spatial continuity, which basically means that the time series that belong to the same field share some similarity, right? And this property allows us to define a new vector, which is called V, a weight vector. And using this vector, we are able to incrementally compute the sign vector. So ZT plus 1 could be computed directly of ZT without referring to the input matrix. The last step of our algorithm is the anticipatory termination, right? And we propose a new algorithm that would anticipate the search of the sign vectors. So what you see on top is basically the normal incremental process. And basically, what we have here is the anticipatory termination. Basically, what this part says that using the signs of those weight vectors, right, we can basically anticipate the termination, right? And then we are sure if we terminate at this step that the final sign vector will be exactly the same, right? So this technique is time and space efficient, it's linear with the length of time series, is incremental, and more importantly, it's correct. So we evaluated our algorithm against the state-of-the-art recovery techniques, and we used different missing patterns. So in the first scenario, we consider that only one time series is incomplete, and we vary the missing rate. And the other scenarios, we assume that multiple time series are incomplete. So we take the first example of basically one incomplete time series. We delete from 10 to 80% of the time series from at the tip, and we recover the block using different techniques. And we use the RMSE as the error metric, right? And what you see in red are the results of orbits. So orbits is on average 25% more accurate than the other techniques. And if you look at the results of orbits, you would notice that the RMSE follows different trends. For example, here, you increase the size of the missing block, and yet our technique gets better. We run some efficiency experiments. We vary the length and the number of time series. The results show that our technique, or confirm that our technique is linear with basically the length of the series, right? And if you take 10 time series, each one has 500K observations. It takes 1.4 seconds for our algorithm to recover 10% of the whole time series. To summarize, orbits is an efficient incremental solution to recover missing values. Our anticipatory termination can be extended to other matrix decomposition techniques if they are applied to time series, and we plan in the future to apply our technique to repair anomalies. Thank you for your attention.